Imagine you live at a time when the Earth's oceans kept receding and intruding on land. I would be panicked, would you? Yeah, you probably would. And building on that, and you might not think this is relevant, how old do you think coal is relatively? And building further on that, how old do you think forests are, specifically swamp forests and peat bogs, which peat bogs are really, really useful for absorbing carbon since, yeah. Well, guess what? We're talking about the Carboniferous period. Yeah, talking about the Carboniferous period today. So, welcome back. If you are following along, thanks. Glad you're staying for my rambling. Anyways, today is the Carboniferous period. So, it was known for like the coal that we use today. That coal was formed back then, and the Carboniferous period lasted between 309 wait, hold on. 359.2 to 299 million years ago. So, that is a relatively long geological period, I have to say. It's very expensive. Anyways, it's mainly famous for swamp forests, coal, and peat bogs, what I said in the intro. But you might think, oh, well, how did they form, peat bogs? Nah, because dead plant material would decompose completely. You're wrong about that, I have to say. Sorry. Anyways, because of the wet environment, it like waterlocks the organism. No, not the organism, the dead plant material, which prevents like bacteria from getting, well, yeah, from getting oxygen. So, no aerobic respiration. So no like lower rates of decomposition, and the dead plant material doesn't completely decompose, and it becomes peat instead, which stores up a lot of carbon. So if you burn peat, that is a big, 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 big problem. Um, and then back then in the Carboniferous period, ocean levels fluctuated a lot. So when oceans covered swamps, ocean sediment built up. Eventually, heat and pressure transformed the peat into coal. So what most places are burning now is just old peat, summarized, but it's just compacted over millions of years. Anyways, continuing on about the Carboniferous period. It separated from the Devonian, which was the past geological period, from the appearance of conodonts, which are an extinct family of fossils that have like teeth or jaws like hagfish or primitive eels. So, for example, today the closest relative is are lampreys, and hagfish. If I think I talked about this before in like a previous episode. They're like fish that could go into brine pools at the bottom of the ocean because there was high salinity in those brine pools, and so they were more dense and could not like diffuse and conjoin, quotation marks, in some ways with the ocean. Those are hagfish. Hagfish can go in there, but if they go in for too long, they get shocked. Like, chemical shock, not like electrical shock, obviously. There's no current or anything down there. Lampreys are like parasites that latch onto big fish. Mostly, yeah, big fish. Big organisms and just draw the blood out of them. Kinda freaky if you ask me. Anyways, the Carboniferous period can be separated into the Mississippian and the Pennsylvanian. Notice how they're American? Yeah, because Carboniferous was literally, like, it was founded in America, I'm pretty sure. Yeah. So, Mississippian and Pennsylvanian. There we go. And now I'm going to talk a lot in detail about those two. Now, the Mississippian environment in North America was mostly marine. So there was a lot of limestone during the Mississippian, including coral fossils. But fossil records from the Mississippian also show that the era was mostly like shallow epicontinental seas, which covered the USA. So, yeah. And then it's also characterized by shallow water limestones. And some of these limestones are comprised of crinoids from shallow seas. There are also other types of limestones, such as mud limestones, which are composed of carbonate mud produced by green algae. And then there's also oolithic limestones, composed of calcium carbonate in like concentric spheres produced by high wave energy. I have to give it to geologists. That is a good job, well done, right there. Big applause. That is a lot. Anyways, the Mississippian strata, so like stratigraphy, yeah, something. I can't think right now. Strata, yeah. Also includes sandstone, which is like quartz sand cemented by silica or calcium carbonate. And then there's also siltstone, which was rock that included hardened silt. So, as you can tell, paleontology, all about that geology. Look at that rhyme. Paleontology, all about that geology. Anyways, the Pennsylvanian, which is like part of the later Carboniferous, so Mississippian and then the Pennsylvanian. Both of them made up the Carboniferous, if you wanted that summary. Anyways, Pennsylvanian was both terrestrial and marine, along with the transgression and regression of the seas caused by glaciers. This allowed for the formation of coal. So what I said earlier, the fluctuation of the oceans was caused by the fluctuation of the glaciation. And when the ocean covered peat bogs, there would be sediment put, like, literally plopped on, well, not plopped on, there would be deposits of sediment onto the peat bogs, which would eventually build up, and cause heat and pressure, like enough heat and pressure for the peat bogs to become coal. That's what happened. And then, and now fossil records from the Pennsylvanian characterize the era by pollen and spore prevalent from the swamp forests, as well as fusulinid foraminifers. Nailed that. Absolutely nailed that. Now, you might be thinking, what's the difference between these two, other than one of them is older and one of them isn't? Oh, yeah, one of them isn't. So, the Mississippian differentiates from the Pennsylvanian by the appearance of the conodonts, if you remember, like, lampreys, eel-like with the weird teeth. Yeah. Such as, this is a really hard name to pronounce. Declinognathodus, noduliferus, and the amnioid genus Homoceras, and foraminifers, Millerella pressa and Millerella marblensis. Yeah. But this only applies to marine deposits, so is it actually completely accurate? Maybe, maybe not. There's also a different reason, like a different Oh, yeah, a different reason. Well, no, a different way to how they are differentiated. So the Mississippian and Pennsylvanian is also characterized, like the differentiation between them is also characterized by a transition from a marine to a terrestrial environment. So pretty significant. Um, over the course of like over 100 million years, the world just fluctuates between ocean, land, ocean, land, ocean, land. That's quite a lot. Anyways, Carboniferous Permian boundary. Now we're the Permian is the next geological era. So stay tuned. You know, Carboniferous Permian boundary is characterized by the appearance of fusilland forams of. Ooh, that is a long name. Schwarina. No, that is horrible. I'm so sorry. I have difficulties just, Sphero-Schwargarina fusiformis in Europe. That was the only one in Europe, and now we're going into the one in America, which has, okay, let me try. Pseudo-Schwargarina beedi. That was a bit better. Anyways, that one was in America, and then the fusillands. Wait, fusillands are giants among protoctists. So like the protoctists, so are like single-celled organisms. So for example, amoebas, those ones, and could reach a centimeter in length. So that is pretty impressive. They were abundant enough to form large deposits called rice rocks because they looked like the fusillands, and also they looked like rice grains. So, yeah, cute. Yeah. Anyways, there were a lot of ecological, geological, biological, and climatic events during the Carboniferous. One significant biological advancement was the development of the amniote egg, which allowed the further domination of land animals, particularly paving the way for the ancestors of birds and mammals. So, essentially, it's a chicken egg. Hard shell on the outside, protecting the amniotic sac on the inside, which then protected the embryo that was growing, with the yolk attached to it, so it had some nutrients. So this kind of like let animals dominate land more, but also, prevent fears of the growing embryo from drying out. Because back then, like before the development of the amniote egg, organisms were probably born in water, in eggs, and in water it's fine, it won't dry out, it won't die unless it gets eaten, or something else happens. But with the amnio egg, you can conquer land, you get food, you get protection. That's practically all you need as an animal. You also need water, but that need wasn't developed yet in the egg. So, and then geologically, the collision of the Laurasian and Gondwana plates produced a belt of the Appalachian Mountains in Northeast America, and then they also produced the Hercynian Mountains in the UK and the Ural Mountains in Russia. So there's a lot of activity in this period. We like that. We live for that. There's actually so much to cover in this. The Carboniferous climate is more humid and tropical than what we had today, and the seasons were indistinct. So, yeah. I don't think I would want to spend a summer there because I think I would absolutely, die of heat exhaustion. Carrying on. Fossil evidence show that Carboniferous plants share the same characteristics to plants that live in tropical and mildly temperate areas today. So that just kind of suggests they're the same, you know? Yeah. And then many trees don't show rings and trunks, which suggested a uniform climate, which may have been the result of large oceans surrounding all land masses. So, I mean, a lot of scientists today use proxy data, which is like data that doesn't necessarily have numbers, I think that is, to see the levels of CO2, back in the geological times. So they use ice cores, ocean sediment, tree pollen, tree rings. They also use tree rings, but that doesn't apply to here because the trees didn't have tree rings. So, yeah. And then there was a lot of shallow, warm marine water, which often flooded the continents. Filter feeders such as bryozoans were abundant, and the seafloor was dominated by brachiopods. So a lot of those mollusks, I don't think brachiopods go into the same family as mollusks, because mollusks are mussels and stuff. So I correct my mistake. I retract my sentence. Anyways, trilobites became increasingly scarce, whereas foraminifers became increasingly abundant. So that just says the foraminifers were more advantageous in the ecosystem. They were more adapted to the changing environment, so they kind of just threw the trilobites out of the food web and not essentially took their place, but they became a part of the food web instead of the trilobites. The Devonian armored fish became extinct and were replaced by more modern-looking fish, which is heartbreaking because I love the Devonian fish. The uplifting during the late Mississippian caused large amounts of erosion during creating deltas and floodplains. The deltaic environments supported fewer corals, crinoids, blastoids, cryozoans, and bryozoans, which were all previously abundant during most of the Carboniferous. So the ecosystem wasn't favorable for them. It just wasn't it for them, simply said. Freshwater clams made their first appearance, there was an increase in gastropods, bony fish, and shark diversity. So that may correlate to the warmer atmosphere, which, warmer waters. As tectonic plates moved, and this movement eventually formed Pangaea, which is I have to say, the most famous supercontinent. Well, there's other ones, but okay. There was a reduction in the coastline, so, there was an increase. Wait, hold on. Leading to a reduction in ecosystems of shallow water-dwelling organisms, and so these species began to decline. These food webs quickly fell down, ecosystems shattering, not literally, figuratively. Yeah, I'm saying it metaphorically. Anyways, I talked about glaciation before. I talked about glaciation before on this. And well, I'm going to go into more detail, so sit back. There are 2 large sheets of ice at the South Pole, which stored large quantities of water, and because there was a lot of water being stored as ice, there was a lot of water taken out of the water cycles. So when there was a lot of glaciation, the water levels fell, but when there was less, water levels rose. So this led to um, fluctuations in sea levels, as I said. And this is seen by striped patterns of alternating shale and coal layers on the surface of rocks during the Pennsylvanian. So that's how scientists, geologists saw that. It's quite interesting, I have to say. Yeah. Anyways, the uplift of continents led to an increase in terrestrial habitats during the Pennsylvanian. So yeah, there was a like a very significant distinction between the Mississippian and Pennsylvanian. Pennsylvanian, it was more, it was more terrestrial and marine. Mississippian, it was moreover just marine, coming from the Devonian. So, um, swamp forests were widespread. It included seedless plants. There were seedless plants. God, like copsids. Yeah, like copsids, which flourished and made up the main component of the characteristic coal that's found during the Carboniferous. There were other types of plants, but this was mainly the most characteristic one. But they underwent major extinction after a downward trend in population, which could be the most reasonable explanation for this is the glaciation caused by the Pennsylvanian. So very, very sad. Yeah. And then as I said, a lot more other plants. There were also ferns and sphenopsids, which became more important during the late Carboniferous. I have to say, they kind of overtook the lycopsids, figuratively, obviously. I'm paraphrasing it. And then, what else? Yeah. The Carboniferous was the revolution for the trees, I have to say. Because before the Carboniferous, it was just small ferns, small plants, fungi. That was it. There was some algae, I think. There were vascular plants, definitely. And then, the earliest relatives of conifers first appeared in Carboniferous. So, big revolution for plants. Plants are old, but if you put this in perspective, sharks are older than trees. Yeah. Sharks are older than trees, fish are older than trees. Technically, jellyfish. I think jellyfish are older than trees. And I also think cephalopods. Cephalopods are definitely older than trees. And I rechecked jellyfish, that family is older than trees as well. So crazy. Yeah. Where was I? Yeah, I am there. Anyways, also a lot of milestones on land as well. Yeah, there were tons of milestones anyways on land. Anyways, first land snails appeared on land, as well as insects that can't retract their wings. So for example, dragonflies and mayflies. So a lot of biodiversity already on land. And then these in particular insects flourished. These insects, as well as scorpions and millipedes, became really important to the food chain, food web, ecosystem. They became really important. They became a solid part of the ecosystem. And I didn't put my notes together. I didn't organize them very well. Anyways, I'm gonna add on to what I said about the amnio egg, there was a lot of drier climates, aridity, and an increase in terrestrial land meant that the production of an amniotic egg became more advantageous for reproduction. So that's a main reason why organisms back then made amnio eggs. Um, so you might be asking, oh, what's the first animal that laid eggs? It's kind of like, what came first, the chicken or the egg? But anyways, the first amniote fossil was Hylonomus. Yeah. It was pretty small. It looks like a gecko. It's yeah, it looks like a gecko, but it's prehistoric. There were basal tetrapods, so the first animals that came onto land. Like between the transition between land and water, so they were kind of semi-aquatic. Became more diverse during the Carboniferous. So there were a lot of predators with long snouts. They had short limbs and flattened heads. For example, Timo T, Team Spondylus, which were similar to another family during the Carboniferous, which was the amphibiamus. I'm butchering these. I'm sorry. And then there were also anthracosaurs, which were basal tetrapods, and amniotes with deep skulls and slender bodies, and these appeared during the Carboniferous. So practically, some of these were the ancestors to crocodiles. And like one idea I want to do in the future for this podcast is look at, the development of crocodiles over time, because there have been like fossil records of gigantic crocodiles who terrorized dinosaurs. So that in itself is exciting. And then I also want to talk about like the evolution of sharks over time. Have you seen those airplanes that have a radar that looks like a pizza on like more towards its tail? Yeah, a shark used to have like that pizza shape on its head. So, that's really interesting to see. Anyways, these animals, like these organisms, were soon followed by the diaspids, which were, essentially, reptiles, but excluding turtles. They aren't being very inclusive, I'm kidding. They were characterized by two orbital fenestrae, which were openings behind eyes. So technically, it includes birds, but excludes turtles. So, yeah. The diaspids were, divided into two different groups. So, the first group, includes marine reptiles, lizards, and snakes, whereas the second group includes archosaurs, which were crocodiles, dinosaurs, and birds. Birds are crazy. They were, yeah. I mean, the modern day dinosaur, uh, yeah, evolved from all of that into a chicken. I have to say, it's a bit counterproductive. Anyways, presumably after the diaspids came around, the synapsids came around. So humans are synapsids, so like tetrapods, practically. But then, the anapsids, turtles and tortoises, they finally have their own name, came around. But the oldest fossil record for these two, like, Animalia families are from the lower Permian. So there may be evidence, it may be possible that they are from the, Carboniferous. particularly the late Carboniferous, like late Pennsylvanian, but there's records showing that they're from the lower Permian, so I wouldn't place all my bets on it. So this is the end of this episode. This was I had a lot of notes for this, but I'm surprised I didn't stretch it long. But anyways, I have an idea of every 4 episodes I take a 2-week break. I think that's pretty good since I have school and everything. And I have to balance stuff out, balance extracurriculars and school. So, yeah, 2-week break after this, I come back and I talk about more stuff. Yeah. Blabbing my head off. But anyways, thank y'all for staying along if you did stay along. Thank you. Oh, right, I have to talk about this. So I take all my information from research journals because I'm a student in A-level. I don't know any of this. I'm learning, and I'm also learning by talking to y'all. So, it helps a lot. I have actually retained some information in my mind about the past geological periods I talked about. So, let me talk about the sources I used today. So, my first source, really long, Carboniferous Period from ucmpberkeley.edu. It's written by... Alright, the original concept was Ben Wagner. I'm sorry if I pronounced that wrong. Published 1996 July? Yeah, that's the format. July the 2nd. But then it was rewritten and recompleted by Angela Ho, Azalea Jose, Ray Mayberry, and Connie Yu. When was this? 1999. May? Yeah, May the 11th. And then I also have two more. So stick along. So this one was about the egg. I talked a lot about the eggs. Titled Introduction to the Amniota, also from ucmpberkeley.edu. So written by Brian Spear, August 1995, but it was reformatted by Dave Smith, June 2009. And then there's also a third one. Hang on. Third one is called what is it called? Diapsida. Even though the page might not show that it's Diapsida, it is Diapsida. It is what it says on the link. So it is Diapsida. Anyways, written by David Pauly, Rob Guralnick, Alan Collins, John Hutchinson, and Brian Spear between 1993 and 1997. So thank you guys. Thank you to the people who I just talked about for providing this information so I can talk about it further. Thank you. That's the end. Again, as I said, 2-week break. So, gotta balance my stuff out. Anyways, bye. Thanks for sticking.